Hey guys, for this video, the part 2 of chapter 4, I'm going to go through some of the other subchapters, and we're going to start off with 4.5, which is mass, a measure of inertia. Mass, measure of inertia. And remember last time we defined inertia as the tendency for objects to keep doing what they're doing. So a tendency for an object at rest to stay at rest, and an object in motion wants to stay in motion. So inertia, objects want to keep doing what they're doing. Okay, think of that. And so now we go here, and it kind of gives an example with an empty can, or a can filled with sand, and a can filled with nails. Now, obviously, the empty can will fly when you kick it; it'll go boom, like off there. But the can full of sand it'll maybe just tip over, and then the nails will just hurt your foot, right? It will hardly even move. And so this is because the mass, when you have an empty can, okay, or a bucket here. Let's say this is a bucket, okay. When you have an empty bucket, the mass isn't very much. Why? What's mass? Mass is basically the quantity of matter in an object. Quantity of matter inside. Let's say inside. So in this bucket, we have hardly any matter. We just have air, so it doesn't have very much mass. Here in the sand-filled bucket, we have some good sizable sand, right? But now in this bucket full of nails, the nails, they themselves have more mass than the sand. So if it's filled to roughly the same height, it's going to go maybe just move a little bit over to the left, whereas this might tip over, right? So basically, when we look at these different examples, each one has more mass than the last, okay? And each one, in turn, goes a shorter distance. So what do you think this means? If we're applying the same force to each bucket, this must mean that mass is a measure of inertia, right? So the more mass something has, the more inertia it has. Mass up equals inertia up. It's not actually an equation. I'm just kind of pointing that out. When mass goes up, inertia goes up, okay? And so this bucket doesn't have a lot of inertia, so yeah, a little force will send it flying because it doesn't have that desire to stand still. This sand has a little more desire, it has a little more mass, so it has more inertia, so it has more of a desire to stay where it is, so it's not going to go as far. And then these nails, it really wants to stay down, it really wants to stay put. So you're going to need a huge force to send it flying, okay? But since we're not applying a very large force, it's not going to go flying. And so that's what they mean when they say mass is a measure of inertia. Just remember, when mass goes up, so does inertia, okay? And vice versa, down and down, okay? Just intuitively. Now we also look at mass is not volume. So basically volume is defined as the amount that something can hold, the amount that a container can hold, okay? This bucket has a volume, okay? But I can fill that with anything I want, and the mass will be different. I can fill it with styrofoam, and it will have hardly any mass. I can fill it up to the brim with styrofoam, overflowing with styrofoam, but it will still go flying because styrofoam has very little mass. I can fill it to here with sand, and it won't go flying because sand has much more mass than styrofoam. It's just definition. And so now they do have a pretty good example of a pillow versus a car battery up there, top right of page 49. The pillow is clearly bigger, so clearly you can fit more matter inside of it. But if you really think about it, the volume of the pillow is larger than the volume of the battery, of course, right? We have a pillow here, okay? It's a terrible pillow. But then we have a car battery here, okay? Look at the size difference. Look at the size differences. Volume is much bigger here. Volume is much bigger in this pillow. But really, which one do you think has more mass? The car battery is full to the brim with chemicals and metal and just nasty stuff, but it's full with heavy items, and car batteries are heavy. Pillows I can pick up with my pinky, okay? Which really has more mass? Now, no, mass is not weight. But which do you think has more mass? Just intuitively. Obviously, The battery, right? The battery has more mass, even though the pillow has a larger size or volume. Now we move on to, they say mass is not weight, which, I'm sorry, I might have made it a little confusing when I was giving the example of picking it up with my pinky. Not weight. I'm sorry. Mass is not weight, okay? And first sentence, mass is often confused with weight. I gave a very bad example, but mass is often confused with weight, okay? So weight is also another way of saying, weight is another way of saying the force of gravity on an object. Force of gravity on an object. Okay, so I weigh 150 pounds, alright? So with me, 150 pounds, right? Now, really, what I'm saying when I say, yeah, I weigh 150 pounds, what I'm saying is that gravity pushes down on me with a force of equal to 150 pounds, okay? I'm not saying that I'm just me physically, I'm 150 pounds. What I'm saying is gravity pushes down on me with 150 pounds of force, okay? That's what it means. That's just what it means. And so now, mass doesn't mean that. If I don't know what my mass is as a human being, but if I did know, it wouldn't be equal to the force of gravity upon me. That's a good distinction between mass and weight, okay? Mass, quantity of matter within an object, right? Okay, so that's cool. Now here's a good sentence. Right below the two definitions of mass and weight, it says, while mass and weight are not the same, they are proportional to each other in a given place. Objects with great mass have great weight. Objects with little mass have little weight. This is where my example with the car battery and the pillow come in. The car battery has more mass, which most likely in most cases means it has more weight. It's harder to pick up, which is true. Gravity acts with a stronger force on the car battery than it does on the pillow, and that's a fact, okay, because it has more weight, right? Weight is the force of gravity on an object. So we move into the new unit we use called newtons. Newtons really are a measure of force. By definition, they're a measure of force. But what did we just learn? What did we just learn? Weight equals a force. Weight is a force. So we can measure weight in newtons, right? Newtons, okay? And newtons is abbreviated with N, capital N, because it's someone's name. So that's key to know, right? And so basically 1 kilogram, this is 1 kilogram, let's say, I think they give an example in the book, it's a bag of nails. 1 kilogram is equal to 9.8 newtons, or N. So you could just do that conversion factor. If you have 2 kilograms, it would be 2 times 9.8, which is what, 19.6, I think. 19.6, I don't know. Yeah, 19.6. So yeah, newtons. Okay, so that's important to know. It's and it's roughly a quarter of a pound. 1 newton is a quarter of a pound, I believe. Yes, 1 newton is a quarter of a pound, and 1 kilogram is 9.8 newtons. So that's something good to know. And then we look. The book mentioned that weight is proportional to mass, and that equation is simply given by weight is equal to mass times the acceleration due to gravity, or just g. So let's say my mass, or let's say my weight is 150, because we already established that, and then I have m, but then my g, we know, since I'm on Earth, g is 10 or 9.8, so then just divide out 10, and we know that my mass is 15 kilograms, right? Just that's simple algebra there. So that's something to know when you're dealing with mass and weight. And then I guess I'll have to do a part 3 for the rest of the subsections in chapter 4. So